What is crack-a-lacking? I didn't really say that. Okay, so next, velocity time graphs. So displacement time graphs, so hopefully fairly straightforward. It just shows how your distance from a point changes over time. If you've moved in one direction, then that's the positive direction, and then maybe if you're the other side of it or behind where you started, then you would have a negative displacement, whatever distance you are away from your original point is how it's measured. In this case, it will be velocity time graphs. So again, we can have negative velocities. The difference is that this would show the change in how fast we are going over time. So our speed, but again, if it's a negative velocity, it means you're kind of reversing in your car instead of going forwards. So something like this top graph here, if you've got a flat line, then that just tells you that you are still moving. Now with displacement, that means you're staying in the same place because you're not getting further away or closer to where you were originally. For velocity, it means you're still moving, but you have a constant velocity, so you're just not speeding up or slowing down. You're just going at the same speed, same velocity, sorry. For the next one, down here, you can see that the velocity at the beginning here, so whenever we started measuring when time was 0, we usually call that u. We then, a little bit of speeding up, so we accelerated up to our velocity there, we tend to call it v, over that period of time, and then the time that it took us here, I'll call that maybe little t. Down here, that's the time that it would have taken us to get from our initial speed to that top speed there, between u and v. And that then is a period of acceleration. So our speed is, our velocity is increasing. So that's acceleration. Then for a period of time, we just have a bit of a constant velocity there. So we just cruise control on, stay at that velocity, nice. And then at a certain time, at a certain point, we start slowing down, we decelerate at that point. So all the way down until our velocity is 0, so there we've actually stopped, we've come to a stop. So we put the brakes on until we've stopped, maybe something like a traffic light or something like that. Okay, so the two important things here from the graph, really the only two things that we need to know about these graphs is that the gradient, so that's the difference in y's, well your y-axis here represents velocity, so the difference in velocities over the difference in x's, which represents time, so however long you've taken there, the gradient is your acceleration. You need to remember that. The gradient represents your acceleration. Also, the distance travelled is the area under the graph. If you can work out the area under the graph, they usually, maybe you can split them up into different shapes, maybe triangles or trapeziums, things like that. If you can work out those areas, then you can work out the total distance travelled in that period of time. So, for example here, if I could work out the area of this kind of sideways trapezium that I've got here, then that would give me the distance I've travelled in this period of time there, however long that was. That would give me how far I've travelled there. And the gradient there, so the v, difference in y's over difference in x's, so the v minus u over t would give me the acceleration, the gradient there would give me the acceleration. Let's have a look at a quick example then of how these work. Very similar. Here, the velocity time graph below represents the journey of a car travelling from one junction to another. Okay, so like a good little driver, it was stationary, the velocity was 0 at the one junction. It sped up until it was going 15, that's probably 15 meters per second. Stayed at that velocity then constantly for 20 seconds. Then decelerated, coming to a stop there. We don't know how long that took, from 30 seconds to however long, but it then came to a stop, I'm assuming, at the other junction. Okay, find the acceleration of the car during that period of time. Okay, so what's the rate of acceleration in the first 10 seconds? Again, acceleration is just given by the gradient in this case. So your difference in y's, well, it goes from 15 to 0. over the 10 seconds. I'll do the 10 minus 0 as well for you there, but it basically speeds up 15 meters per second in 10 seconds, so that's 1.5 meters per second meters per second squared. So that is our acceleration. If you can work out the gradient of the graph, then that will give you the acceleration. Given that the car decelerates at 3 meters per second, so we know then that the acceleration from t is 30 upwards. So that part there, the deceleration, is 3 meters per second. Find that value of big T. Right, cool. We should be able to do that. And again, you literally only have two things you can use for these graphs, either to do with the gradient and the acceleration, or the area travelled. Sorry, the distance travelled is the area under the graph. And so because we're talking about deceleration, then it must be the gradient malarkey. So again, the gradient of this is difference in y's, so it was 15 down to 0. So difference in y's over difference in x's, which would be t minus 30, whatever that distance is, whatever that time interval is there, the difference between those two. And that should equal 3. That should equal 3. So hopefully with a bit of rearranging, we can get an outcome. So we get 15 equals 3 times t minus 30. So 3t minus 90 is 15. And then hopefully you can see if that minus 90 that I get there, if I bring it over to be add 90, that will be 3t is 105. Divide by, sorry, I'm running out of space. Divide by the 3, so t should be 35 by the looks. T there is 35, 105 divided by 3. Yeah, good maths, John, well done. Relatively straightforward. All to do is just our gradient formula, difference in y's over difference in x's, or difference in velocities over difference in times, because our y-axis is velocity, our x-axis is time. Gives us the acceleration. You could then have a question about find the total distance. Here we go, find the total distance. Now they can ask you per section of the graph if they want, like in the first 10 seconds. If it was in the first 10 seconds, you would just have to work out the area of this triangle here. That will give you that. However, they say the total distance from one junction to the other here, so that's the entire graph. What's the area under the entire graph? Well, this is just a big trap, a big trapezium, and we should be able to work out the area of a trapezium. We know that it is, from our formula, add the width of the top and the width of the bottom, divided by 2, multiply by the height of the thing, or the distance between the vertical, the parallel sides. Wow. Okay, so that top width there goes from 10 seconds to 30 seconds, so that's just 20 seconds wide. That's 20 wide. Ooh, sugar. My displacement time, how about that? And then the bottom we've just worked out is 35 seconds altogether, so that's 35 wide. So hopefully then we can get the area, which is given by top plus bottom over 2 times the distance between them, which is 15. Quick bit of maths, I should have done this earlier. 27.5 times 15 is 275, add 137.5. Correct me if I'm wrong. Should be something like 412.5 meters. All in all, this car has travelled. Yeah, hopefully I'm right there. Yeah, and there we go. That's basically everything we need to know for that. Thank you very much. Bye-bye.